Hi everyone, this is the last video for our absolute value linear inequalities, and even the last video for this unit discussing linear inequalities. In the previous video, we talked about solving absolute value linear inequalities with the symbols for less than or less than or equal. Right now, we just simply change or reverse the operations into greater than and greater than or equal for number 3. So we are just going to solve here again the solutions by coming up with the linear inequality form and then give the equivalent solution set graph in interval notations. But to do this, we need to remember the general format for the absolute value linear inequality involving the symbol of greater than or equal. It is in this form. If the absolute value of x is greater than any constant c, it's a combination of two statements. First, x is greater than positive c, or x is less than rather negative of c. So we use this conjunction or to combine the two statements. This is also the indication. If you would like to review for that, go ahead in the previous video. This is an indication that our solution set, our graph and interval notation should also be two different things combined into one. But then again, please be reminded of that our general format here, the end product of our linear inequality form should only contain x, but not wait, by the way, could only contain a numerical coefficient of 1. Right? My point of this is by applying here this general format for number 1 here. It should take the whole expression as a reminder, so it should become 6x is greater than sorry, that's greater than positive 120. Oh my goodness. Greater than positive 6x is greater than positive 120, or 6x is less than negative 120. Okay. Please look at the general format again. It should be x here. So we need to come up with an expression here that it should only x on this side by dividing this by 6. I will also divide this by 6 here. Okay. This is also true for the second statement. Divide this by 6 and then divide this by 6 here. And then that could cancel out as well as here. And then we come up with x is greater than positive 20, or x is less than negative of 20. Again, we do this process because our general format or for linear inequality form is where our coefficient for x is just simply 1. And we could also check this. We could actually use 21 here. 6 times 21 as we substitute in our given is actually 126. And the absolute value for that is greater than 120. We could also use negative 21. 6 times negative 21 is negative 126. The absolute value of negative 126 is positive 126, which is still greater than 120. This would mean that this linear inequality form, the two of them combined by the conjunction or, is the correct form. And then after that, we could come up with our solution set, graph, and interval notation. Our solution set, as again, is a combination of two different solution sets. The solution set for this and the solution set for the second statement. So you have set of x such that x is greater than 20. And the second one is set of x such that x is less than rather negative 20. But they're different. Uh, there are two different solution sets, but we need to come up with a notation that they should be combined into one. As a reminder, the term or the conjunction or will just be changed into an operation using the same conjunction in set operations, which is actually the union of sets. So this is now the solution set, the combination of both. If we're going to go back again to the less than notations there, they are actually joining in between. But since we have two different statements here combining into one, our graph should also be like that. We have two different graphs into one real number line. We start first by graphing this. The starting point is 20. It goes towards the right. So you place here arrowhead rather. And then we open 20 because 20 is not included. It could not satisfy the inequality form. Finish this with a parenthesis here. The second graph on the same real number line is all about the second statement here. We start with negative 20 and we go to the left now. Left because the symbol of inequality points towards the left. And then negative 20 is still not included. Okay. And we use here parentheses as well. So as you can see, the graph here goes or points towards two different directions. That should be your analysis and your guidance when you come up with a graph, because we notice here that we have two different statements combined into one. You don't need to place union here, because by placing it in one real number line, that would mean you're already combining them into one. But we are going to use that union again as we come up with our interval notation for these two regions. We have negative infinity to negative 20. Please do not interchange. If it is always open, and we use here parentheses, so this is also open. The second here, we start from 20 and we go to positive infinity. This is open still and open here as well. And to combine them, simply use the union. So let's continue with item number 2. In item number 2, we have a binomial here. Don't worry, simply apply first the general form. So you will have here x minus 6, that's minus, it's too long, is greater than 3, or x minus 6 is less than the negative of 3. Again, greater than positive of the constant or less than the negative of the constant. We simply follow that one. And then again, we will not divide here, but we are going to add 6. Not divide, but add 6 on these sides and add 6 here on these sides as well. Okay, this will become 0 and we will be having x only, and it's greater than 3 plus 6, which is 9, or x is less than negative 3 plus 6. Please check your integers because that is actually 3. Okay, so all values greater than 9. Let's start with 10. 10 minus 6 is 4. Absolute value of 4 is greater than 3. Correct. Less than 3 here, you may choose 0 if you want. 0 minus 6 is negative 6. Absolute value of negative 6 is positive 6, which is greater than 3. This would mean that our notations here are correct. And then our solution set should be the combination of set of x such that x is greater than 9 and set of x such that x is less than positive 3. When I say combination, we do union. Okay, the graph will be separate and independent graphing of this in the same real number line. We start here by 9 and we have here 3. Of course, definitely they should not be interchanged. They should not be written like that, because if you're going to interchange them, that would mean 9 is smaller than 3. Do not do that. Please make sure that you follow the notations. So 3 here and 9 here. All values greater than 9, arrowhead, and 9 is not included. Because if you're going to try to substitute here 9, 9 minus 6 is positive 3. Absolute value of that is still positive 3, but it's not greater than the value here of 3. That would mean 9 is not included. 3 here is also not included, because if you have 3 minus 6 is negative 3, absolute value of negative 3 is positive 3, but it's not greater than 3. So we also open here, but we start from 3 and we go to the left, use arrowhead, and we make it open here. Okay. And complete it again by parentheses. That's it for our graph. And the interval notation, it will be patterned from the regions shaded here. So you have negative infinity to positive 3, open, open, union with open of 9, positive infinity, always open. Okay? So please be guided with that. Let's have our last example. This last example, we may again combine the understanding of item number 1 and item number 2. But first, let's apply the general format. So you have 2x plus 5 is greater than or equal to positive 7, or 2x plus 5, that's 5, sorry, is less than or equal to negative 7. To do this, we are going to treat this as a simple linear inequality where we start first by subtracting 5 on both sides here. This would also be similar here, subtracting 5 on both sides. Subtract, not divide. So you will have here 2x is greater than or equal to positive 2, or you have 2x is less than or equal to, check your integers, negative 7 minus 5 is negative 12, right? And then divide here by 2 as well as here. Same thing will be applied here. So you have, that's canceled out. So you have x is greater than or equal to 1, or x is less than or equal to, sorry, I have made here, added here something. Yeah. So negative 12 divided by 2 is negative 6. You may want to check that one. I would try to use 2. 2 times 2, because that's greater than 1. 2 times 2 is 4, plus 5 is 9. Absolute value of that is greater than 7. We could also identify already if 1 is included or not. Substitute here, 2 times 1 is 2, plus 5 is 7, and the absolute value of that is equal to 7. Since we have equality here, that's already okay. So that's already okay here. And then you have negative, less than negative 6, or you have negative 7. Let's try negative 7. 2 times negative 7 is negative 14. Plus 5 is negative 9. Absolute value of negative 9 becomes positive 9, which is greater than 7. This means that these two are now acceptable as 1. And then come up with the solution set x such that x is greater than or equal to 1. The OR becomes union. You have x such that x is less than or equal to negative of 6. The graph, we have two graphs. Here is negative 6, again, the smaller value, and you have here 1. 1 goes up rather, to the right, arrowhead. What is different here is just we simply shade here 1. Sorry for the spill. And we will shade here 1 because 1 can be substituted here and still make the inequality true. For negative 6, let's try. Negative 6 times 2 is negative 12. Absolute plus 5 is negative 7. Absolute value of negative 7, though it's not greater than 7, but it's equal to positive 7. That would mean 6 is also included. I started already with the inclusion. Don't worry. It goes to the left as indicated here. And then we have arrowheads. To complete that, bracket and bracket here. That's it already for our graph. Finally, for our solution set, the region here is between negative 8 to negative 6. Infinity is always open, but negative 6 here uses bracket, so it should be closed. 1 here uses bracket, and we have positive infinity, which is always open. And then you combine them by union. So as you can see, we are not already assured that as soon as we apply the general form, we could already come up with a correct linear inequality form. So look at number 3, 1, and 2, especially number 3. You need many steps applying the properties of inequality to come up with linear inequality form having a variable with coefficient of 1, numerical coefficient of 1. Okay, so Regardless of whether we have finished this, I have shown you how to do this. Try to re-answer it on your own. You already know already what the answer is, or what are the answers. But it would be better if you will try it and come up with the same answers as ours. Okay. So this now covers the whole of unit number uh, 3 rather, for absolute value linear inequalities. So we will be having our assessment soon, covering the whole of unit number 3. So please prepare and please practice in advance. Thank you very much. See you soon. Goodbye. Stay safe.